All right, in this video, I'm going to continue with California housing dataset and show how we can implement linear regression on that dataset. Make sure that you watch the previous video in which I walk through how to clean this dataset and prepare it for regression. The very first step that I'm going to take in this video is to basically create two datasets that include my features and the labels. So the very first thing that I do is to basically create my features dataset denoted by capital X, and that would include all the columns except the label dataset. And if you recall, the purpose in this practice is to predict the median house value column. Therefore, that is my label, and the features should include all variables except that particular label. So what I have to do is to use my main data set and then drop the column that includes the median house value, and make sure that you copy paste from your variable names such that so that you won't make any typos. So basically what I'm doing here is that I'm creating my features dataset, which is the X dataset that includes all the values in the original dataset except for the column median house value. And just to make sure that we've done it correctly, we're going to print the head and take a look at it, and you see that median house value is not defined properly. Let me see what's the error. Oh, I had to put it in the quotations here. All right, now you see that this data set is exactly like the housing clean data set, except the fact that you do not have the median house value. Now, the other thing that I have to do is to create my label dataset, or my Y in lowercase dataset, which is again going to be housing clean, and the only thing that it has is going to be the median house value. So this is my Y dataset, and let me just print this as well. You see that you only have the median house values. This dataset, the Y dataset, only has one column that includes the median house values. All right, now let me also comment this. Instead, I'll say that we are creating features and label datasets. Now, once we have created this, we are ready to go and split this data in these datasets into training and testing datasets using the train test split. So like before, we go and type in from sklearn dot model underscore selection import train test split. And then we just type in xtrain and xtest. And then we have ytrain and ytest, which is going to be equal to train test split. Then what is the features dataset is called the X. It's the one that we just created. And then the labels dataset is going to be the Y. And then I am going to create or make a split in which 20% of the data is in the test data set. So test size equal to 0.2. And then in order to be able to recreate this results, I'm going to identify a random state as, again, as always, 1984. You can use any other number that you want. Just going to run it to make sure that there is no errors here, which there isn't any errors. And now, let's go and import the OLS regression model. So we go in and type in from sklearn dot linear underscore model import linear regression. So linear regression is the function from the sklearn, which we're going to import. And, in the videos about linear regression, we talked about the fact that it is called ordinary least squares, or in short, OLS. And I'm going to call this linear regression function OLS because it's much easier to refer to it going forward. So I just say OLS is equal to linear regression. Make sure that you open and close the parenthesis. And now I can go ahead and actually fit my models by using the fit feature or attribute. So I said say OLS.fit. And just like before in all the other models, I have to identify the features and label dataset of my training. So, and those are X train and Y train. So let me just run it. Let me see, I have a problem here. Linear regression. And the problem is that this L is in small case, so I have to make sure that it's in capital case. And now you see that the linear regression runs. So just like before, when you just fit a model, then the model is fit in the background and the results are not displayed. What we have to do here is to display the results. And what I want to look at is the intercepts and the coefficients and the R-squares, right? And the way that I just do it is to go ahead and say, let me just comment this, display the intercept and coefficients of the OLS model. And I go ahead and say print OLS dot intercept. And again, please remember that in the video about the basics of the OLS regression, I told you that when you're regressing, you're basically defining a line, and the intercept is, how far it is from the origin, how far the y is away from the origin. Is it positive or is it negative, right? So that is the intercept of that particular regression line. So OLS.intercept don't forget the underscore at the end. And the intercept is this value. And you can make it a little bit nicer and add the description here. Say that intercept is plus, and remember to change this OLS.intercept into a string value. And then you would see that it is written that intercept is, and then also let's type in print OLS dot coefficients, and this would print the set of all coefficients for you. You see that this is basically an array, and you can say the set of coefficients are, and then add the plus sign and turn this into a string. So it says the set of the coefficients are as follows. And finally, you can create the R squared. And I will discuss the R squared in the next video. It's basically a measure of performance of the OLS regression. And that would be OLS.score on X train and Y train. And let me just say print. And that is actually the value of r squared, but just like before, in order to make sure that we have a description, we are going to add it. The r squared value is, and then add plus and str here and here. And it would type the value of the r squared for you. Now, as you can see here is that, there are two problems that we have here. The very first problem is that the results are kind of very difficult to interpret and understand. They are not printed in a nice format, which I'm going to explain how to overcome using some other functions shortly at the end of the video. And the other problem is that we haven't visualized anything yet. So let's think about how we can visualize the results from the OLS regression. Well, the very first thing that we can do is to actually make some predictions based on the fitted OLS model. And once we have those predictions, we're going to calculate how far off we are from the actual value, right? That would be the difference between the predicted value and the actual value. And then once we have that error, we can use that in order to visualize the performance of our model. So I'm going to create a new block and call it predicting with OLS, and it's very easy. I can just type in OLS dot predict. I'll make sure that you are typing incorrectly. And what we are going to predict based on is the test data set and the feature portion of the test data set. So what this does is basically uses the test data set in order to make predictions based on the set of features in the test data set. And I am going to put the results in a column called y_pred. So basically y_pred is going to be a single column that includes or contains the predicted values based on the test data set. And once I have it, I am going to create a new data frame that puts the actual value and the predicted values side by side. So let me just type it here, and I'm going to call this performance. And then the performance data set is going to be pandas data frame, which you have to use the data frame feature in order to create. And what basically I am going to say is that, hey, put the y predictions and the actual values of the feature of the label into this data set that I call performance. And this would work, but what I want to do and make it a little bit nicer is to create names for these columns so that I know which one is which. So for y_predicted, I'm going to call it predictions, and for y_test, I would call it actual values. All right, and now let's take a look at the performance data frame. Okay, let me see what the problem is here. Okay, I have to put this here. Okay, now it works. So you see that you have the predictions, which are the actual labels in the testing data set. And you also have the, you have the actual values, which are the actual values in the testing data set for labels, and then you also have the prediction. So for example, for this particular observation, the actual value of the median house price has been $328,200, and the predicted value is $315,646 and change, right? So the difference between what I want to do is to calculate the difference between the actual values and the predictions. And in this particular case, we're doing a pretty good job in terms of predicting something that is very close to the actual values, right? And so let me go ahead and print this before this head. So I'm going to just say, basically create a new column and call it the error. So the error column in the performance data frame is going to be equal to the difference of the actual values and predicted values. Let's see. Oh, again, I forgot to put it into these things. They don't need the parentheses. Yeah. Okay, after you fix all the typos that you may have, you would have this. So this would be the difference between the actual values and the predicted values, which is defined in this new column called error. Okay, now what I want to do is to create basically a form of a bar chart in which this error value is plotted on the x-axis, and the x-axis should be the number of observations shown by an index. And you see that the index is actually the original index from the original data set, and since the testing data set is a random sample of the original data set, you see that these index numbers are not continuously one after each other. So what I want to do is to remove this, create a new index, and then turn that index into a column so that I can use it in my next plot. So I'm just going to create a new block here and just call it preparing data for plotting. And it's very easy to do. So I just say this performance, and I'm going to use the attribute of reset index. So reset underscore index is going to reset the index for you. And you have to first drop this, the existing one that you have, because this is not what we want. So I just said type in drop, and then you type in place is equal to true to turn it into a column. And then you got to, again, use the reset index attribute for the second time, and just type in place is equal to true. And what in place option does is that it turns your index, as you can see, is just an index right now. You see that there's no column names on top of it, into an actual column, right? And then let me copy and paste the here so that you would see the results. So you see that there is an index column added into your data set, and then you also have your index feature. The interesting thing about it is that it starts from 0, right? Previously, it was some number that did not have any meaning for you, but now it starts from 0. It's basically counting the number of observations. And it's also turned into a column. So you see that this index column is the new column that you have in your data set. So now we're ready to actually go ahead and plot this. I'm going to call this block plot residuals. And well, the very first one is to define a figure. So we just say figure is equal to plt dot figure, and we identify a size for it using the fixed size. So let's say it's 10 by 5. And once we have it, then we can actually go ahead and plot the bar chart. So that would be with the bar attribute. So plt.bar. Now, what is going to be your x-axis? Well, the x-axis is going to be the index. So we are going to define index. And what is going to be the y-axis? The y-axis is going to be your residuals, basically, or your error terms. So you put in error, and then you have to give the name of the data set based on which you want this bar chart to be created, or basically the source of this index and error variables, and that would be your performance data set. And I'm just going to define the color to be black, and also the width of the bar charts to be equal to, say, 0.3. And before, let's just actually show this to see what we have here. Okay, so this is what we have. There is a bunch of things that we can do. The very first thing is that we can add the titles for the y-axis and x-axis. So let's go ahead and do it. So what I'm going to do is to say plt.x label, which is going to give a label to my x-axis, is going to be called, say, observations. And I'm going to also give a label to my y-axis and call it residuals. So let's run this again to see the results. And you see that the label observations and residuals is now added to your model. Now, the other thing that I want to do is to reduce the number of observations that are plotted. Basically, here you can see that it goes over 4,000 observations that are put into the testing data set, and it makes this plot, kind of very difficult to understand. So what I want to do is to actually go ahead and zoom in on, let's say, the first 50 observations. And the way that I can do it is here when I am identifying the data set based on which I want the bar chart to be created. I can identify that I only want the, say, first 50 observations by identifying this value here. And then when I run it again, you see that it's zoomed in. So it's much nicer. And what does this plot is showing you? What is this plot is showing you? It's basically showing you whether you're underestimating and overestimating each value in your testing data set, right? And remember, the error that you defined was basically the difference between the actual value and the predictions, right? So when the error is positive, it means that you are making a prediction that is less than the actual value. In other words, you are underestimating. Whereas where the error is negative, it means that you are overestimating, right? So here you can see that this is a positive, meaning that what you have predicted is less than the actual value. Therefore, you are underestimating here, whereas in these three observations, you're overestimating and so forth, right? So this is a nice way to visualize the performance of your model. Of course, the best OLS model is the one that has an error terms of 0, meaning that this is a straight line and it's centered on 0. Of course, that model is very, very difficult, if not impossible, to build. But that would be the perfect model. And the taller these bar charts are, the further away you are from predicting the actual value. So a good model is a model that has shorter bars. Now, one other thing that I want to do is to display the OLS regressions that was displayed here in a nicer fashion, right? In an easier to understand fashion. And that is based on a new set of libraries that we're going to use right now. So you have to go in and import statsmodel.api. So just type in statsmodel.api, and I just call it SM as short for stats model. So this is a specialized library for all these statistical models, right? And one thing that you have to do is to basically do a very small fix on your data set. And this is what I do. I just type in xtrain is equal to statsmodel.add_constant. And then I define the xtrain. So what this does is that it basically comes and adds a constant equal to 1 to your training data set, right? Let's see if I have x_train dot head. Oh, sorry. Statsmodel.api. Statsmodels, sorry. Okay, you see that originally the xtrain dataset did not have this column constants, right? And I said that when you do this, when you type in sm.add_constant xtrain, there's going to be a constant added to your dataset. It is necessary if you want to run an OLS regression model using the statsmodel.api library with an intercept. Okay, so this is a necessary step that you have to do in order to get identical results to the linear regression model in sklearn, right? So just type that and make sure that you're adding the constant to your xtrain data set. And once you have it, you can basically go ahead and use the OLS model in the stats model data set. So what I'm going to do is type in sm.ols, and the syntax is that you have to give it the name of your training data set first, and then basically the name of the labels first, so Y train, and then the name of the feature. It's the opposite way of the sklearn regression model. So you just type in Y_train and then X_train, and remember this X_train is the version that includes a constant variable, right? So sm.ols Y train and X train, and then in the syntax, the other thing that you have to do is to add .fit, and I'm going to call this my OLS or nicer OLS model. Okay, so nicer OLS is the one that is defined in the stats model library, and it's going to fit my model. And once I have fitted, I just go and just type in nicer OLS dot summary, and let me run it for you. And you see that once you run this model, the results are presented in a much nicer way for you to interpret. Now, just one thing to verify, you see the constant here is estimated to be negative 2.147. That is your intercept. And let's go and compare it with the results of the sklearn model. You see that the intercept is negative 2.1467 something. That is the exact value that you have here, negative 2.147. And you remember that it is multiplied by 10 to the power of 6, right? So that is exactly the same number. Right? In other words, let's see the last factor. Near ocean is negative 1.4, and that should be the last. Here you see that this is the last coefficient here, negative 1.4, and so forth, right? So rather than displaying the results in this very difficult to understand manner that you don't know which coefficient is corresponding to which variable, the stats model OLS function is going to present the results in this very nice and easy to understand manner. So you have the estimated coefficient, standard error, t statistic, the p-value, and then the confidence interval.